Hi everyone. What we're going to do now is section 7.8, which is an introduction to what are known as improper integrals. What this covers is integrals where there are vertical asymptotes involved, or where the area that we're looking at runs out to infinity. And that might not seem like a case where we can make sense of an integral, but it turns out if we're willing to use limits, we can. Our motivating example is going to be the function the integral from 1 to infinity of 1 over x squared dx. And we can interpret that as an area by thinking about its graph. So the function 1 over x squared looks like this. And we're saying that we would like to start at x is equal to 1 and then consider the area under this curve that goes like this forever. Now you might think that what that means is because the curve runs forever, that the area underneath is infinite as well. However, you should notice that for any value of t that I choose, so just pick some value of t out here, that the area contained here, that is the integral from 1 to t of 1 over x squared dx, is equal to minus 1 over x evaluated from 1 to t, which turns out to be 1 minus 1 over t. So the area in this region is 1 over 1 minus t for any value of t that I choose. And in particular, that continues to hold if I let t go out forever towards the positive infinity. So we could say that the limit as t goes to infinity of 1 minus 1 over t, well, that limit is 1. So what we can do is we can interpret an expression like this as an area of an infinite region, and we say that that makes sense as long as the limit that we compute turns out to be a finite number. So what we're going to do is we're going to make a definition that says that the integral from 1 to infinity of 1 over x squared dx, what we mean by that is really the limit as t goes to infinity of the integral from 1 to t of 1 over x squared dx, and then that limit turned out to be the thing that was equal to 1. So we're going to use this as a shorthand notation for the process of applying a limit to a regular integral. This is the first class of what we call improper integrals. If you want to know why we use the word improper, remember that if I want to use the fundamental theorem of calculus, which says that the integral from a to b of f of x dx is equal to f of b minus f of a, where capital F is an antiderivative for little f, I can only do this under these conditions. AB has to be finite. So I'm not allowed to have an interval that runs out to infinity and then plug in endpoints. And 2, f has to be continuous. Now, there are ways that you can break this up with what are called removable singularities, where maybe the function is defined in one way and then it jumps and it's defined some other way. But the pieces have to be continuous. In particular, what that means is no asymptotes. So let's look at an example with a vertical asymptote and see if the same kind of behavior could happen. What if I had a function that looked like the integral from 0 to 1 of 1 over the square root of x? Now the problem is that 1 over the square root of x is a function that looks like this. And we're trying to look at the region in here. We have the same problem, which is that there's this asymptote that's a vertical asymptote, which means the function gets closer and closer and closer to it, but then it rips up to positive infinity here. And the question I have is, could this also possibly be interpreted as an area that makes sense? And we're going to use the same exact approach. We're going to pick a value of t. We're going to notice that for any t that I choose, the integral from t to 1 of 1 over the square root of x dx is equal to 2 root x evaluated from t to 1, and that turns out to be equal to 2 minus 2 root t. Now, that holds for every t between 0 and 1. What happens if I let t get closer and closer and closer to 0 as long as I'm doing it from the right-hand side? The limit as t goes to the 0 from the right of 2 minus 2 root t is equal to 2. So this area is also an area that can be meaningfully interpreted even though there's an asymptote involved, because there's this limit that makes sense. And so what we say is that the integral from 0 to 1 of 1 over the square root of x dx, which is really secretly equal to the limit as t goes to 0 from the right of the integral from t to 1 of 1 over root x dx, that this is equal to 1. And so we say that that integral makes sense. So those are the two cases that we're going to be dealing with that are improper integrals. Two different cases corresponding to two different ways that we're breaking the fundamental theorem of calculus. We're taking intervals that run out to infinity, and we're also going to look at functions that have vertical asymptotes. Type 1 improper integrals are easy to identify because they have infinity as a limit of integration. So what we say is that the integral from a to infinity of f of x dx, that's going to be a quantity that makes sense if the following conditions hold. 1, the integral from a to t of f of x dx exists for every t bigger than a, and the limit as t goes to infinity of the integral from a to t of f of x dx is defined. So two conditions need to be met. First, this integral had better make sense for any intermediate t that I pick between a and infinity. And second, when I compute it as a limit, the limit has to exist. If those conditions hold, we say the integral from a to infinity of f of x dx, which is equal to the limit as t goes to infinity of the integral from a to t of f of x dx, is convergent. So this is a definition that we're making. You should never think about infinity as a number that can be plugged into a function, because it's not. The infinity represents a limit that we just don't want to write every time we write the integral down. The fact that we've used infinity here is shorthand for the fact that this is a limit expression. And all of this only makes sense if this limit makes sense. Now, I'm not going to try to pick on engineers here, but in classes in the past that I've been affiliated with, there have been people, particularly in engineering classes, that have felt comfortable throwing infinity around as a number that you can just stab into a function. The problem is, and you should be able to see this if you know anything about L'Hopital's rule, is that infinity as a quantity, when you start plugging it into functions, you can get ambiguous results. Infinity over infinity could be 0. It could be infinity, or it could be any number in between, and there's no way to know. So infinity represents limits. So we can define integrals that have negative infinity as a limit of integration, or both limits of integration as infinity in the same way. So we could also say the integral from minus infinity up to a quantity b of f of x dx. So we're going to say that this makes sense if 1, the integral from t to b of f of x dx exists for all t less than b, and the limit as t runs off to minus infinity of the integral from t to b of f of x dx is defined. And if that's true, then we say that the integral from minus infinity to b of f of x dx is equal to the limit as t goes to negative infinity of the integral from t to b of f of x dx. Essentially what we're doing here is we're making a picture like this, where we have some function. We're saying here's b, and the area that goes off to the left here, we're saying is equal to an integral I can write down if I interpret that as a limit. And I'm saying this has to be, for every t value you choose, this area has to make sense as you move t forever to the left. And then not only that, but the limit has to make sense as t runs off to negative infinity. The final case is where both of the limits of integration are infinity. And there's not going to be anything surprising about this definition. It's exactly the same. So for this one, we are going to define this to be equal to the integral from minus infinity to c of f of x dx plus the integral from c to infinity of f of x dx, as long as both limits exist. And I should point out here, c can be any number. And so frequently it's useful to let c be equal to 0 because it's easier to compute with. So again, I want to explicitly point out that when I write down this and this, I really mean that those are not integrals, they are limits of integrals. These are limits. You cannot work with these without working with limits. Okay, so let's look at some simple motivating examples and see if we can figure out if these infinite areas make sense or not. So we already know that if I took the integral from 1 to infinity of 1 over x squared, which I can immediately interpret as the limit as t goes to infinity of the integral from 1 to t of 1 over x squared, that this was convergent. So maybe any function that's asymptotic to the x-axis will be convergent when I take its integral. To test that, let's look at the integral from 1 to infinity of just 1 over x. Since this is only going to make sense if it's a limit that converges, the first step I'm going to do is I'm going to rewrite this as the limit as t goes to infinity of the integral from 1 to t of 1 over x dx. Because remember, you can't even use the fundamental theorem of calculus unless a and b are finite. If you try to use the fundamental theorem of calculus here, and you dare to plug infinity in as a limit of integration, I'll break out my red pen. Don't do that. Okay, since I have a finite integral here, then that means I can compute with it like regular. This is the limit as t goes to infinity of the natural log of x evaluated from 1 to t, which is the limit as t goes to infinity of the natural log of t, which is infinity. So this is divergent. Since the limit doesn't exist, the integral is said to be divergent. This is not a quantity that makes any sense. From the geometric standpoint, what you're saying is, if you have the function 1 over x squared, which looks like this, and you have the function 1 over x that looks like this, that 1 over x is also asymptotic to 0, but it doesn't get close fast enough to make this area finite. So something about what we're measuring here is how quickly 1 over x squared tends to 0 as compared to 1 over x. Okay, another example. Let's look at the integral from minus infinity to 0 of x e to the x dx. Now, I can look at that and think, oh, it's going to be an integral by parts, which is great. We can do that. But remember, I can't do anything to this involving regular integration rules until I rewrite it as a limit. So this is the limit as t tends to minus infinity of the integral from t to 0 of x e to the x dx. And now I can use integration by parts. U is equal to x, du is dx, dv is e to the x dx, v is e to the x, and all of this gets replaced by the limit as t goes to minus infinity of x e to the x minus the integral of e to the x, and all of this is going to be evaluated from t to 0. When you do that and the dust clears, what you end up with is the limit as t goes to negative infinity of 1 minus t e to the t minus e to the t. Now the limit of 1 is 1. The limit of this part, I have a piece that's going to infinity and a piece that's going to 0. A quick application of L'Hopital's rule will show you that this tends to 0. This is by L'Hopital. And this tends to 0 because e to the negative huge is 1 over e to the huge, which is 0. So this entire limit turns into 1. And that means that this integral is convergent. If you want to think about it in terms of functions fighting each other, what's happening here in the original integral is we have a function x, which is trying to run away to negative infinity, and a function e to the x, which is trying to run away to 0 as you head to the left. And the question is, which function wins if we're piling up all this area underneath it? Well, e to the x tends to 0 so fast that that crushes the area down to the x-axis so quickly that it forces this integral to be finite. Okay, so let's look at another example. This is a cute one. Let's look at the integral from minus infinity to infinity of 1 over 1 plus x squared dx. So this is a double-sided infinite improper type 1 integral. What I'm going to do is pick a convenient value of c and then split this up into an improper integral that runs out to the left and an improper integral that runs out to the right. And the convenient value of c I'm going to choose is going to be 0. So I'm going to rewrite this as the integral from minus infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx, where these are both still limits. So I need both of these limits to converge if this is going to make any sense. So let's start with the first one. The integral from minus infinity to 0 of 1 over 1 plus x squared dx, I am not going to succumb to the temptation to do anything until I've rewritten this as a limit. Now, if I'd like to, I can use my standard rules of integration because the fundamental theorem of calculus applies, and that says that this is equal to the limit as t goes to minus infinity of the arctangent of x evaluated from t to 0, which turns out to be equal to the limit as t goes to minus infinity of the arctangent of 0, which is 0, minus the arctangent of t. So what does the arctangent of t do as t runs to minus infinity? The graph of the arctangent looks like this. And it has horizontal asymptotes at pi over 2 and minus pi over 2. Pi over 2 as you head to the right, minus pi over 2 as you head to the left. And so all of this is just equal to pi over 2. If you do the same argument on the positive integral, what you're going to end up is that this is equal to positive pi over 2, because the integral from 0 to infinity of 1 over 1 plus x squared dx, in order for that to make sense, I have to rewrite it as a limit. Now I can use the fundamental theorem of calculus. The arctangent of 0 is 0. The arctangent of t is the arctangent of t. But now I'm taking a limit as t runs off to positive infinity, and that means that this is all equal to pi over 2. So what have we shown? We showed that the integral from minus infinity to infinity of 1 over 1 plus x squared dx, which we broke up into the integral from minus infinity to 0 of the same integrand, well, each one of those limits turned out to be a convergent integral, and you get pi over 2 plus pi over 2, which is pi. This is the basis for a type of function called a probability distribution, one of the probability distributions, because the function 1 over 1 plus x squared looks like this. It crushes down to the x-axis fast enough that it bounds the area in such a way that you get a total of pi units of area contained underneath this graph. So when we're doing these types of improper integrals, one of the things we're measuring is how fast we get this asymptotic convergence to 0 in the function. If the functions go to 0 fast enough, that traps the area so that it has to be finite.